Okay, so we're back here in the Dropbox folder for Lecture 5, and now I'm going to discuss the Predator-Prey Advanced model. So I'm going to open up the model in Vensim and just show you a little bit of the interaction. And I think the first thing that you'll notice is that this model is a lot more complex. I will spend some time going through the model structure. Perhaps I will skip a few of the details, like going through every single dialog box to look at the units. I'll let you certainly do that, and you can see that I have here a preset graph, and I don't know if it's going to show yet because we haven't run it. Um, the model has again rabbits and foxes, so foxes being the predator, rabbits being the prey, and I want to walk you a little bit through the structure and also show you a couple of interesting features that are introduced in this model for you to see how they look like. Let's start with the rabbits, and the rabbits have a rate of birth and a rate of death. The rate of birth of the rabbits, it's in this model had the specific intent of inserting a sort of a disturbance into the system. Okay, I'm going to explain to you what that is. If you go to the equation, if you go to the birth of rabbits, you will see that there is the birth of rabbits is equal to the population of rabbits times the birth rate. Okay, plus something that here it's the test of increase, and test of increase is another variable, and I'm going to get out of this just to show you where that one is. And this is a new way to introduce a disturbance that's called a pulse. And the idea here is that in this system, in this model, there is a pulse of rabbits that's introduced after time equals 10 years for a duration of 0.5, for a duration of 6 months. So, and the size of the pulse is 100 rabbits. So the idea is that here is that there's an intervention, and the intervention is to add a sudden pulse of rabbits into the system. Okay, we're going to see what the impact of that is. So that's one of the features in this model. Now, the other thing you notice that the birth rate of rabbits that appears, it's now here given as a something that's referred to as a lookup table. Okay, and you will see that there is there's two variables. There's a variable that's called relative population, which we'll discuss in a second, and then there's a notation I use, table 2. There's also a table 1 for the foxes, where essentially the birth rate of rabbits, which is given in rabbits per unit rabbit per year, so it has units of 1 per year. It's a table function. It's a lookup table function. Okay, and I want to tell you how that is introduced now. Now, this relative population that feeds into the birth rate of rabbits, it's a ratio of population of rabbits per a new variable that is defined in this model, that's sustainable population. Okay, so the idea is that you look at the rabbits as they compare to some population, and this could be a target population, or in this case is being called sustainable population, some value, which in this model is equal to 500 rabbits, as you click back to the equation for the sustainable population. So let's see. We have a sustainable population of 500 rabbits. That sustainable population allows us to calculate a ratio of the rabbits to that sustainable population, and that tells us through a table what the birth rates of rabbit is. Now let's take a look at that table. That table is T2, okay, and it's got a format, and you can actually look at the Vensim documentation for more details. But basically, the first in brackets, the first couple of numbers here indicate the range of the table. Okay, and the range of the table it goes from 0 here to 2 for the independent variable, which in this case is a relative population. So we're looking at relative populations in the range of 0 to 2, okay? And then we're looking at the tabulated value of the birth rate that is going to be somewhere between 0 and 4, okay? Now the actual values are given as a series of points: 0, 4, 0.5, 3.5, 1, 2, 1.5, 1, 2, 5, and 2, 1. And that basically means that for a relative population of 0, the birth rate of rabbits is 4, okay? For a relative population of 0.5, it is 3.5. For 1, it is 2. So for a relative population of 1, when the population of rabbits is equal to that sustainable value, it's 2. Now, if the population of rabbits exceeds the relative population by 50%, so that their ratio is 1.5, the birth rate of rabbits drops. And if it reaches 2, so if it doubles, then it reaches a value of 1. Okay. Now the units of this, of course, are in. If you go back to the birth of rabbits, are in rabbits per year. Okay. So if you multiply, if you look up the table, that's going to allow you to calculate the birth rate of rabbits. And the birth rate of rabbits feeds into the birth of the rabbits. Okay. Jointly with the pulse. So essentially, what's happening here, if you think about it now, if you put everything together, is that the rabbits grow because of two things. There's this increase, the pulse, and then plus this birth of rabbits. But the birth of rabbits is dependent on how the rabbits compare to this sustainable population, this target, which in this case is 500 rabbits. Okay. So that tells us a little bit of the dynamics of the growth of rabbits, and that's a little bit of a more complex picture that we had before. Now the death of rabbits, it's handled here in slightly different manner than we did with the previous predator-prey model. Here the death of rabbits, it's going to be dependent on, and this is another introduction, because these rabbits are being hunted, okay? So let me actually walk back through that. The rabbits are being hunted by the foxes, okay, for eating, but that rate of consumption of rabbits, which leads to their death, it's driven by a dietary requirement of foxes, and we're going to walk through that in a second. So, if we look at the dietary requirement of foxes, it's got units of rabbits consumed per each fox per year. That value is 25, and I put a little comment here. So this is the number of rabbits eaten per fox in a year. Okay, so that's their requirement, and so that requirement feeds into the hunt for rabbits, which is the number of foxes multiplied by the dietary requirement of the foxes. So that when you multiply those two, you get units of rabbits per year. Okay, so that gives you this value, and that is going to result in the death of rabbits. Now the death of rabbits, so rabbits can die for two reasons. A, they die naturally, okay, or B, they're consumed by foxes. So the death of rabbits is going to be the maximum, and this is the introduction of a function in Benson that chooses the maximum between two values. The value of the hunt of rabbits, so this is the amount of rabbits consumed by foxes, or another possibility is you take the population of rabbits and you divide it by the average life expectancy, and that gives you another. So this will give you the natural cost, and the maximum of those two is what dictates the actual death of rabbits. Now, in this model, the average life expectancy of a rabbit is 2 years. Okay, so either a rabbit dies after 2 years, thereabouts, or is eaten before by the foxes, and that's a little bit of the dynamic of the demise or the decrease of the rabbit population. Let's take a look at the foxes. Okay, so the foxes in this model can be born, and the birth of the foxes is handled much in a similar way as the birth of rabbits. It's essentially a lookup table where the birth rate of the foxes, it's a table T1, and it's a function of relative population. And the understanding here, and this is a very similar to the one we saw in the Lotka-Volterra model, is that the availability of rabbits, this relative population, it drives the ability of foxes to grow. So what you have here now is that the relative population drives the birth rate through this table. In this table, let's take a look at it now. It's a table. It's the same format. You have a range here in brackets. So the table goes from 0 to 2 again in the relative population. So we're assuming that the population of rabbits is always somewhere between 0 and twice the sustainable value of this 500 that we have there, but we can change that. And then the T1, the growth of foxes, it's somewhere between 0 and 0.6. Okay, and then if you look at the values, and these are actual values: 0, 0.5, 1, 1.52, and then for the growth rate, 0, 0.12, 0.25, 0.27, 0.3. So that's the range in which the growth rate of the foxes moves. Okay, so that dictates the foxes, and then the foxes die also, and the only reason that foxes die is natural causes in this model, and it's driven by an average life expectancy of 4 years. So that's after 4 years these foxes die, or at least on average. So that is essentially a rundown of this model dynamic. You can see it's a lot more involved. So let's take a crack and run it. And so if you do that, here you have the preset graph for the rabbits, and then you can see, interestingly enough, that it's prior to. Let me actually zoom into that. I'm going to zoom maybe to 100. No, it's too little. We zoom to 200, and that's going to be big, but at least it'll allow me to see the graph in a lot more detail here. Okay, so you can see actually that you get again this oscillatory behavior. Okay, goes up and down. It starts at 500, so it starts at the population, and then remember that we introduce, and I'll show you the graph in a second, a pulse at 10 years. We introduced this pulse that was 100 rabbits, so it went up, and then it starts oscillating after that. So the reason it goes up is because of the introduction of that pulse. Okay, so let me zoom back to the fit screen, and let's take a look at the graphs for other variables. So if we look at the rabbits will do essentially that we just saw. Okay, that's the same graph. Let's look at the foxes and see. Let's take a graph of the foxes, and just shade them there so they appear there. So the foxes also, because of the introduction of the rabbits, they seem to be dormant or more or less steady at the beginning at 40, their initial value, and then they start to oscillate. Okay, the oscillations are not as big, and it goes up to maybe 42 rabbits, and then comes down back to 40, and it goes back and forth. But it does introduce an oscillatory behavior. I think it's probably interesting to look at the test of increase in a graph, and you can see the pulse here. Okay, so the pulse was at 10 years for half a year. So for 6 months, you introduce 100 rabbits, and then the pulse died away. So it's a sudden introduction of rabbits into the system to see how they affect the remainder of the dynamics. Okay, and you can actually start playing around with it a little bit if you want. Let's see, what else can we see? Let's take a look at the. We can actually do anything. Let's look at the hunt of rabbits and see how hard they're being hunted. You can see here that this is the rabbits hunted per year over time. And you can again see this oscillatory behavior. Typically, when you have a system where one of the variables is oscillating, that means that probably the remainder of the variables are going to be oscillating too. It's only natural that if things move in, shake in one direction, they shake also in other variables. They don't have to they don't have to oscillate in sync, as we saw in the Lotka-Volterra model. There is a lag. There could be a phase or a lag between the oscillations, but it will oscillate. We can look at the, let's see, we can look at the birth rate of rabbits, for example, and we can do this pretty much for any variable. We can click and look at the plot very quickly. The birth of foxes, same deal. Again, oscillations. They don't have to be all nice, but as long as they're regular, they sort of look the same. You can do that. I think one thing that I wanted to show in this model that I didn't show in the previous one is how to build those plots. So you can actually go to, if you go to Control Panel, one thing before we do this, sorry, is let's look at the model setup. It's always good to look at the setup. And again, it runs for 100 years. It's running at a time step of 1/10 of a year. Okay, and you can actually change that if you want and see what the impact is, and you can play around with this a little bit more. So I wanted to say that. But let me go to the Control Panel and just see how you can define. You have all these variables here. You can define graphs, and I defined a graph that's called foxes and rabbits, and this is the same graph that was defined in the previous one, but I want to show you how it looks like. And if you click on it, and it'll display it, and this is the one that shows the the populations together, okay? And you can actually edit all these things. You can edit the time span, you can edit and I'll show you how to do that in a second. But this is essentially the graph that looks at both populations, and you can see then the oscillations of one versus the oscillations of the other, how they're not completely in sync, etc. Okay. Now I wanted to show you if you select from the Control Panel, select graphs, and select the graph that you want to look at, and say modify in this case. You can see here how to set up this model. You can give it a name, okay, and I call that foxes and rabbits. You can give it a title, which is the legend that appears on top of the graph, okay. And you can in here you can essentially put in all the variables that you want to plot together. And, it allows you to do up to 6 here. I just wanted to do the 2. You can modify the horizontal axis. In this case, it's time. Okay. You can plot time, and you can select the range. And I just said 0 to 100 years. I can change that, and see what it looks like. It's not not a huge deal. And then you can modify all that, and then just redo the plot. So what happens, for example, if we do from 0 to 200, just for the sake of an argument, and do that, and then close here, and then you essentially redo the simulation, okay? And we redid the simulation. Let me pull the plot out again. Oh, I think I probably just had it displayed. I may not have to run this, and then let me get rid of the old one. This is a new one, and you know what? What happened is that we don't simulate past time. So that was a silly exercise. So let's actually redo the simulation now. Going to settings and running to 200. Okay. Now we can rerun, and then we can actually simulate again simply. Just say yes, so it replaces, and you can actually display the new graph. See, and you see revised, sort of the same graph, it just it extends to 200. So I thought I'd show that on this case, as well as let me close this, as well as give you a summary. So we looked at the pulse in the test of increase. We looked at lookup tables for the birth rates of foxes and rabbits, and we also looked at the max value as a function to select between two variables. Okay, so this model has those little upgrades that you can look at. So you can look at all these results. You can modify. One thing you can do also with this model is you can do an input-output object and do the synthetic, the synthetic simulation. Remember, this will allow us to you can overwrite it, or you can change the number. And now, see, you can turn some knobs. Okay, you can turn the sustainable population of rabbits. You can play around with the expectancy life of foxes and rabbits. You can with the dietary requirements, and you can see how the graphs vary. The other thing you can do as well is you can actually go to each of these boxes and actually I changed it dramatically, but I just wanted to actually look at how I think I went too far. And of course, you can see that you start getting garbage when your things are too unrealistic. So that they take it down back to 25. Let's see. You can actually click. Let me do that. If you click on the arrow, you can just fool around a little bit with the size, and we're using 25. I let it vary from 0 to 200, but I can just say let's just vary between 0 and 50 if you want to restrict it, and it's and then then it'll give you less leeway. You can do the same with all of these. 0 and 10 for the expectancy of rabbits. That's probably okay. For foxes, between 0 and 20, that's probably okay. And for sustainable population, between 0 and 3,000, which is probably fine. It's and then you can start running and see what the impact is. Okay, so it's a nice predator-prey model for you, and I hope you can play with it and learn some more. And we'll move on to the next example now.